Hello, dear students. Now we are discussing something more of fuzzy sets. As you have seen in the last lecture, we have just discussed the basic properties of the fuzzy set theory. Now, in this lecture 2, we'll discuss some of the properties of the crisp set, variety of operations which we can perform on the crisp set, and on this background, we will discuss the properties of the fuzzy set and the various operations which can be performed on the fuzzy set. So this will be the content which we will be covering in this lecture. Later on, we will see how much these things are important in fuzzy relations. Okay, so now let us come to the different kind of properties of the crisp set. As you already know that the crisp set is the classical set, and which is having the crisp boundary, deterministic boundary, where the membership of an element is defined, fixed. Either it is 1 or 0. It means either an element would be a member of the set or it would not be the member of the set. Now, come on the basic properties of the crisp set. One is the commutativity, associativity, distributivity. So first of all, come here. Here we are having a set A and set B. We are representing them with the capital letters. So it means they are representing the sets. So A union B is B union A, or A intersection B is B intersection A. It is very simple. You already know. When we talk about the associativity, so here the operations are same, A union B union C, but how we are performing that? First of all, we are making the union of B and C set, and then further we are making the union of this result with the set A. So it will certainly produce the same value as we perform the operation in this sequence. Means if we are making the union of first of all A and B set, and that result has been union with the set C, so they both will produce the same result. The key thing, the important thing to keep remember here is that in terms of associativity, the operations are similar kind, and it also does hold for intersection operation, like A intersection B intersection C is equal to A intersection B, then intersection of C also. So this property also holds. Now terms about the distributivity. When we are talking about the distributivity, so dear students, please do remember one thing, that we will be working on different kind of operations, right? So like here you can see one operation, that is union operation is here, then inside the bracket there is intersection operation, right? Here the another rule, you are saying one intersection operation, and here inside the bracket there is a union operator. So keep remember this thing, distributive law of distribution is very important, and according to it, it says that A union B intersection C is A union B intersection A union C. Similarly, it also holds with A intersection B union C is A intersection B union A intersection C. Next is idempotence, that is A union A is again A intersection A is again A. It is very simple. Identity, law of identity. If A is union with null set, so again it will produce the set A. If A is being done intersection with the universe of discourse, here E we are considering that E is the universe of discourse. So once we are making the intersection between the universe of discourse and some specific set, the result will be the same set, that is set A. Or here what we are doing, we are making the intersection of set A with a null set. Here the result is the null set. When we are making the union of A and the universe of discourse, then the final answer will be the universe of discourse. Next is the law of absorption. So law of absorption says that A union A intersection B, you have to visualize it. A union A intersection B. A intersection B will contain the element which are common among A and B. Now you are making the union of these things with the element of entire A. So it means you can say for example, A is having 20 elements and there are 2 elements which are common. in B also. So A intersection B will have only two elements. When we make the union of these two elements with the entire A set, the result will be the entire A set again. So this is known as the law of absorption. Similarly, we can say that A intersection A union B. So here, what it will do, the result of A union B, it will contain the elements which are either available in A or available in B. When we make the intersection of this set with the set A, that will give only the set A. So this is the law of absorption. Next is the law of transitivity. According to law of transitivity, it says that if A is the subset of B and B is a subset of C, then certainly A will be the subset of C also. So also transitivity is there in the nature. Involution. According to involution, the complement of A is A. Double complement will produce the same set. The next is the law of excluded middle. Law of excluded middle says that the union of A and A complement would produce the universal set. Rather, we can say that the universe of discourse. So here, what we are saying that some elements are there in A, and what will be the A complement? A complement will have all those elements which are available in the universe of discourse except A. So when we are making the union of both of them, it will produce the universe of discourse itself. Law of contradiction. A intersection A's complement, it will produce null set. Then finally we are having De Morgan's law. A union B's complement will be A's complement intersection B's complement. Here the sign has been changed. Here the operation has been changed. If it is union, so here it is intersection. If it is intersection, the final answer is with the union itself. So one another new thing is the partition. So a partition on A is defined as a set of non-empty subsets AI. What here we are saying, AI is the subsets of set A. Set A is given to us. Now we are making the partition of set A. So when we make the partition of set A, so they all would be the non-empty subset. We are representing them AI, which when which are pairwise disjoint to each other. It means what we are saying, they are not overlapping to each other. They are disjoint to each other. Disjoint to each other, we mean to say that when we make the intersection of all these subsets, so in any of the way we will find the null set only. So simply we can say they are not overlapping to each other. So here, suppose say for example we are having a subset AI, another subset is AJ. We can choose any value of I or any value of J, irrespective of any set. When we make the intersection of these subset, the answer will be null set. It means nothing is common among them. They are not overlapping each other. So here what we are saying that if we make the union of all those subsets, that will produce the same set. So they all are known as the partition of set A. They all are known as the partition of set A. So I am just again repeating, partition of set A will be the subset of A, those who are not overlapping to each other, rather we can say that they are disjoint to each other, and the union of all these subsets will again produce the same set A. Now the next thing is the covering. Covering is just similar to the partition, but here the condition is that whatever the subsets we are making from the given set A, they may not be disjoint to each other. It means they can cover to each other also. They may overlap to each other also. So the covering on set A is defined as the set of non-empty subsets AI whose union produces the original set A. So when we make the union of all those sets, it will again produce the same set. So here there is one rule that is known as the rule of addition. According to this rule, it is saying that the cardinality of all those subsets which we achieve from the partition, which we achieve with the help of partition, if we sum up the cardinality of all those partitions, then it will equal to the cardinality of the given set A. Now The next rule is the rule of inclusion and exclusion. According to this, suppose say for example we are having we it is applicable for covering set. For suppose there are two subsets A1 and A2. Here the cardinality of the set A is A1 union A2. Dear students, please keep remember here one thing, that partitioning is not so much important. Partitioning sets are disjoints to each other. In general, in realistic situation, we would not be dealing with the partitions of the set. We will be dealing with the coverings of the set, where the sets will be overlapping to each other. I'm just giving an example. Say for example, there is a team of cricket player. There are some batsmen, but there may be some batsmen, those who are bowler also, those who are having fielding capabilities also. So it means whenever we are talking in terms of a general scenario, so one set also possesses the property of some other set also. So here we can say that there is a kind of overlapping of elements also. So here in our real scenario, we will be dealing with the covering of the sets. So here this rule of inclusion and exclusion is for the covering set. यहाँ पे it is mentioned that it is applicable for the covering set. Now take, we are having two subsets, and that is why I am writing here n is equal to 2, and say they are A1 and A2, and we know that when we make the union of these two subsets, certainly it will produce the same set. And again, when we make the union, and the cardinality of that union will be the cardinality of the given set. But here, how we are achieving it? The cardinality of A1 plus the cardinality of A2 minus cardinality of the A1 minus A2. Say for example, because they are the covering set, they are not the partition. Say for example, in A there are 10 elements. In A, I'm saying that in A there are 10 elements, and in A1 there are 6 elements, and in A2 there are 7 elements. In A1 there are 6 elements, and in A2 there are 7 elements. So here I'm just saying once we make the union of this one, that will come, it will have all the 10 elements. So the cardinality of the union will be again 10. The cardinality of the given set A is 10, but the cardinality of A is 6, cardinality of A2 is 7. So once we make the sum of these two, it becomes the 13. Total becomes 13. So here what we are doing, minus the cardinality of the subset, which is the intersection of these two covering sets. So certainly in that scenario, their cardinality of the intersection would be 3. So how we are getting the final cardinality of A1 union A2? It is the cardinality of the covering set A1 plus the cardinality of covering set A2 minus cardinality of the intersection of these two covering subsets, right? So now here, suppose we are having 3 covering sets of given set A. So here it becomes very important also. Its cardinality of set A will be the cardinality of the union of all these 3 sets. Again, how we can achieve it? Individually make the summation of the cardinality of these 3 covering set minus the intersection of first second minus the intersection of first third minus the intersection of second and third. So here what you did, you can cross check it also with the help of the Venn diagram. Here you will find that one of the portion which is common among A1, A2 and A3, that has been eliminated twice. So for that purpose I am just adding it for finding the right answer. So what becomes the final solution? Cardinality of all 3 covering set minus the intersection of 2 of them, taking the intersection every time with 2 covering sets, and plus adding the intersection of all 3 sets. Okay. You can cross check it by doing the verification. with the help of the Venn diagram. So now I'm coming to fuzzy sets. Friends, as I have already told you in the previous lecture, that our entire objective is to study the fuzzy set. Why we are dealing every time with the crib set and the classical set? Reason is that we may have the some kind of perception in our mind ki if we start dealing with the fuzzy set, we can have the similar kind of concept which can be adopted with the fuzzy sets also. Hmm. So here I told you that the member which is available in the fuzzy set, rather we can say the element which is available in the fuzzy set, it is having one membership value within within that set. That means every element possesses some value, and that value is in a range of 0 to 1. That element may have value ranging between 0 to 1. Ranging between 0 to 1 means if some element is having membership value 0, we can say that this element does not belong to the given set. Still, we can keep that element in the set, but we are having its membership value 0, so it simply is indicating that it does not belong to the set. If some elements are having lesser membership value, like membership value 0.5, 0.25, 0.1, 0.0, 0.01, 0.023, something like that. So we can say that these type of elements are having lesser degree of association in the context of the given set. Lesser degree of association of the elements. And say for example, if some element is having membership value 1, so we can say that it is having the absolute membership. It is having the absolute membership. If some elements are having membership value 0.8, 0.9, so it's also a good value in a range of 0 to 1. We can say that they are having the strong membership. And you already know that vagueness has been introduced in the fuzzy set. Vagueness is introduced in the fuzzy set by eliminating the sharp boundaries that divide members from non-members in the group. Here, there is a special sign which we assign with the set name, which shows that the given set is the fuzzy set. Some authors are marking this, putting this tilde sign above the set, and some authors are marking this, putting this tilde sign below the name of the set. So I am following the practice of having the tilde sign below the given set name. So this itself is representing a fuzzy set. If only this is written A and then the tilde sign is there below this, so it itself is representing that the given set is the fuzzy set. So let a fuzzy set A in the universe of discourse U can be defined as a set of ordered pair with its membership value, and it's represented and is represented by like this. So as I told you that a normal crisp set is represented, it is simply the collection of elements. But here I'm saying that the fuzzy set is not the simply collection of elements. It's a collection of ordered pair. It's a collection of ordered pair. Yes, elements are there in the set, but the elements themselves are having some membership value. So I'm saying here that here A is the fuzzy set. It is a collection of the ordered pair, and here X is taken from the universe, set of universe. Rather we can say universe of discourse. So every element which is available in the universe of discourse, that is available in the given set. Again, it is very strange. So earlier we know that in the classical set we were fulfilling some specific property. Some specific property was also given, and the element, those who will be fulfilling the specific given property, they are coming in the set only. But here we are saying that a fuzzy set is a collection of ordered pair. Pair means element along with its membership value, and we are putting all the elements in the fuzzy set. We are not allowing some specific element. We are allowing every element to come in the set. Every element in the context of the universe of discourse. So elements which are available in the universe of discourse, they all are available in the fuzzy set with some specific membership value. So this membership value may be 0. if some element is having membership value 0, that means we can say that that member does not belong to the set. But most of the time, we again are not interested to give exactly the membership value 0. We may give very lesser membership value to these kind of elements. So the membership value ranges from 0 to 1. So that membership value is represented with the help of mu. So here, to represent the membership value, mu symbol is there. Mu x means we are having the membership value of x element with respect to the given fuzzy set A. So here it becomes a ordered pair. The fuzzy set A is a collection of ordered pair of element and its membership value of the same element with respect to the given fuzzy set A, provided that every element we have chosen from universe of discourse of that context, right? So here another way to represent fuzzy set is that what we can do here A is a fuzzy set, how we are writing it, it's a curly braces and elements are separated by comma. Some authors are writing that they have been separated by the plus sign. They may be separated by the plus sign also. Here I am representing it, I am separating them with the help of comma. In the denominator, I am writing the membership value of x1 with respect to the fuzzy set A of x1 element, comma, membership value of x2 element with respect to the fuzzy set A of x2 element. It means in denominator elements are written, in numerator membership value of those elements with respect to the given fuzzy set are mentioned. So it is one another style to represent the fuzzy set, and here the complete fuzzy set can be represented like this. It's a summation of these ordered pair. It's a summation of these ordered pair. This is not the algebraic summation. This is not the algebraic sum. It is basically said we are not making the summation algebraic summation of all these things. Rather, we are saying that it's a collection of ordered pair where in numerator membership value of the elements are mentioned with respect to the given fuzzy set, and in denominator that specific element has been put. Now these membership value can be discrete in nature and they can be continuous in nature. I'm just discussing this point with you that the fuzzy set which we are making, it may have members which may be discrete in nature, which may be continuous in nature. Continuous, say for example, there are some sensors which are continuously abstracting some information, some data, and along with that we are making some kind of the fuzzification, and by this way the elements which we are having, they may be continuous in nature. So in that scenario, we can represent a fuzzy set like this with the help of the integration sign. Again, it is not the algebraic sum of the information written here. I'm not making the integration of this function. It is the summation of the continuous elements. I'm making the collection of the continuous elements along with their membership value. That's it. Now I'm just coming to discuss the operations, various kind of operations on the fuzzy set. The first operation is union operation, then we will discuss the intersection operation also. Say here, it's a diagram where on the x-axis we are having different elements which are available in the universe of discourse, and on the y-axis we are having the membership value. And as I already told you that the membership value of any element, it may range from 0 to 1. So on the y-axis we are having membership value which are ranging from 0 to 1, right? And here on the x-axis we are having the elements of universe of discourse. So it's a one function, and we are showing its membership value. It's a first set, and it is another set, another membership function is there. It is written here. So how we can make the union of these two sets? Certainly if we are making the union of these two sets, so there will be no problem. So we may have the elements in the union set, but we want to know the membership values of these elements. Suppose A is having some element B. Here we are making the union of these two sets. So they both sets will be working on the same universe of discourse. Both will be working on the same universe of discourse, right? And once we are making the union of them, so we are interested to find the membership value of the elements in the final set. We are not interested to find who will be the member of the in the union set. We are not bothered about to find out the elements who will come in the union set. Rather, we are interested to find out the membership value of the element, those who will come in the union set, right? As I already told you, that all the members are there in the fuzzy set. If somebody is absent, so we can mark them with the membership value 0. So you can consider that that A is having some element, B is having some element, they are working in some universe of discourse, and finally once we are making the union of these two sets, so we are having already all those elements in the union set, but we are interested to find out the membership value of those elements, right? So here the membership value can be represented as membership value of A set union B set. Now this X, this is the element. For this element, the membership value will come the maximum value of mu x, comma mu bx. So whatever the membership value X element is having in set A or X element is having in set B, that maximum value would be considered as the membership value of the union set. So I already told you, we will consider that all elements which are available in the universe of discourse, they are available in set A. If we want to say that some elements are not there in A, so we can put them in A also with the membership value 0, right? Similarly, all elements are there in B. Once we are making the union of these two sets, so here we are interested to find out the membership values of that element, and that value is achieved with the help of this formula, and this is nothing, simply we are getting the maximum value of the maximum membership value. So this X element was there in A set, X element was also there in the B set. However, it may have 0 value in any one of them, right? So we will find the maximum membership value with respect to set A or with respect to set B, and that maximum value will be the membership value of that element in the union set, right? Now I'm just giving you an example here. Say for example, where I mark here P1. Say for example, P1 is an element. P1 is an element. It is available on the x-axis. On x-axis there is a point P1, and on P1, just see here, its membership value in first set A is A1. You see here, it is A1. What I am saying you, that the membership value of P1 in set A is A1. The membership value of element P1 for set B, for set fuzzy set B is, it is A2. You getting my point? So it is A2. So which one will be having the higher value? A1 will be having the higher value. By this way we can find out the maximum membership value, and it will come in the union function, right? Now come on the intersection. So here what we are doing, we are doing the intersection operation of fuzzy set. Two fuzzy sets are given to us. One is set A, another is set B. On the x-axis we are having the elements of the of universe of discourse. On y-axis we are having the membership value, and when we make the intersection of these two fuzzy sets, so we will again have all the elements. With some new membership value, and that the new membership value will be the minimum value either in set A or in set B. So what we will do, for any specific element we will find its membership value in set A, we will find its membership value in set B. Whatever the minimum value is there, that membership value will come in the intersection set. So here the minimum value will be kept, and we take x from universal discourse. Right? Now come on the complement. Complement operation says, say for example, there is a set A, fuzzy set A. So fuzzy set A complement will have all those elements which are in A, but the membership value will be 1 minus the existing membership value. It is very typical to say, very typical to visualize. What I am saying that, say for example, we are having a set fuzzy set A. Now we are interested to find out the fuzzy set A complement. So I'm saying that it will again have all those elements which are available in A, fuzzy set A. This is the difference between the fuzzy set and the classical set. Here in the fuzzy set, the complement fuzzy set will again have the same element, but here the membership value will be different. How we can get the membership value of any specific element? 1 minus the membership value of the given set. So here I am interested to find the membership value of any specific element x for A complement fuzzy set. That will be 1 minus mu ax. Right? So there are some another operations on fuzzy set. One is the algebraic sum. Algebraic sum is sum of fuzzy set A plus sum of fuzzy set B. It will be, we can write it down, membership value of this set we can achieve is mu ax plus mu bx minus mu ax dot mu bx. Algebraic product is mu ax dot mu bx. Bounded sum is when we are making the sum of the fuzzy value of two sets, the maximum value can be 1 or can be this one. If we are getting the value which is more than 1 by adding the membership value of mu x and mu x b, then in that case we cannot have this kind of facility, so the upmost limit is 1. So here what we will do, if its value is coming to more than 1, then we will take the maximum value 1, and if it is having value lesser than 1, we will take that value. Similarly, the bounded difference, in that case what we will take the maximum value, either it is 0 or it is this one. If it is coming to minus, so we will not take the minus membership value. In that scenario, we will take the membership value 0. Otherwise, if it is having some value, we will take that value. So I think that's all for this lecture. In the next lecture, we will cover some another kind of properties which holds for the fuzzy set, and then finally we will discuss something related to how we can make fuzzy set and variety of examples for making the fuzzy set. That's all from my side for this lecture. Thank you very much.